we saw that by mimicking the arguments that were so successful for Bernoulli and Gaussian distributions, which was based on logarithmic Sobolev inequalities, we can actually do something for general independent general distributions for independent random variables. So we have a general function of n independent random variables, and now we don't need to assume anything about the distribution of these, and we can still prove this type of quasi or modified logarithmic Sobolev inequalities. And I should have mentioned that the first one to come up with such inequalities was Michel Ledoux, when he was giving somehow understandable proofs of Talagrand's inequalities, which I will come to a little bit later. Okay, so based on this, we could get such a nice inequality which says that, for example, if we have this type of bounded differences assumption, which relaxed bounded differences assumption, because here we only need that the sum of these differences squared is bounded, and then we saw two examples when we can say something non-trivial about the sum of these squares, even though the individual differences can be quite big. Then we have a Sub-gaussian, the Sub-gaussian tail inequality, where here this V is the number that plays the role of the variance. Right? If we have a Gaussian distribution, then the tails should behave something like e to the minus t squared divided by twice sigma squared. Now instead of sigma squared, now here we have this number V. You can think about this V as the Efronstein estimate of the variance. Right? Because remember, the Efronstein inequality, when we have a condition like this, then the Efronstein inequality tells us that the variance is bounded by V. So we don't quite get the variance, but we get something close, if the Efronstein estimate is good. Okay? So these are really nice. It says that whenever the Efronstein estimate is good, we get a Sub-gaussian tail inequality for free. Well, it's not quite for free, because the Efronstein inequality says that the variance is less than the expected value of this. Here we need more than bounding the expected value. We need to actually bound this quantity almost surely, right? Deterministically. Okay, but you can still think about this phi as an Efronstein upper bound for the variance, and then it will play the role of the variance in this Sub-gaussian tail inequality. Yes?
Maybe it's a dumb question, but could you please tell me about this deterministic expression that you mentioned? Almost sure.
Oh, this is the deterministic one, right?
Could you please explain it a bit? Why do you call it? Almost sure. This is almost sure.
Oh, because so the requirement here is that this works no matter what the values of the function are. Right? So what we assume here is that this is a random variable, right? This depends on x1, x2, xn. Okay. Now this complicated random variable, here we require that it is bounded always by this number v. Okay. If we have such a bound, then we can put it in here. And it will play the role of the variance in such a Sub-gaussian tail inequality. Okay?
Is that what the jargon means?
Sorry?
Is that the jargon almost surely, or?
Almost surely means with probability 1. Almost surely means that with probability.
Deterministic means?
That's the same. For it, in my,
Oh.
right? With probability 1, that means that it happens. Except maybe for a 0 probability event, which we don't care. Okay? All right? Okay. So, yeah. So this was an example in which we could show that no matter what the value of the random variables, the values of the random variables are, this thing, which is somehow this random variable, is always bounded by a constant, no matter what it is. Okay. So, in particular, the variance of the largest eigenvalue is bounded by 16. Okay. That's our Efronstein estimate of the variance, and we get this tail inequality, right? Where instead in place of v now we have this constant 16. Okay. All right, and this was another example when when we could bound deterministically the value of this random variable. And the bound is just the Lipschitz constant. All right. So when we have a Lipschitz function of n independent random variables that are bounded, then we get a Sub-gaussian tail inequality, where in the place of the variance or the standard deviation we have just the Lipschitz constant. Okay. Now here's we had another class of interesting random variables which we called self-bounding. Right? Remember that we had several examples of random variables for which we could prove that had this kind of property that when I leave out one point. Right? Remember, zi here is defined by like this. Okay? So we take. What is this? Yeah, zi is now just any function of the rest of the variables when I leave out the ith variable. Okay. So this is the kind of functions that we call self-bounding. That if I leave out one random variable and I calculate this function, which is often very naturally defined, then this difference, the value of the function can only decrease. It cannot decrease too much. And the sum of these differences is bounded by the value of the function itself. Okay? This is what we call self-bounding. The random VC dimension was like this. The conditional Rademacher average was like this. The length of the longest increasing subsequence in a random sample was like this. So there are many natural examples in which this holds. Okay? What's the Efronstein estimate of the variance? Well, it's just the expected value, right? Because the sum of z minus zi squared is always less than this, and the expected value of this is now less than the expected value of z. Okay? So here, the Efronstein estimate, which is just the sum. Remember, the Efronstein estimate says that the variance of z is less than. Well, in this case, for example, it says that it's less than the expected value of z minus zi squared. Okay? So here, this random variable, we don't bound it by a constant, but we bound it by the value of the function itself. Okay? This is why we call this self-bounding. Right? Now, using the same kind of machinery, starting from modified logarithmic Sobolev inequalities of this type, one can also handle random variables of this type, and you get a kind of different kind of differential and inequality for the moment generating function, but you can still solve it, and what we get is somehow analogs of Bernstein's inequality, where instead of the variance, in Bernstein's inequality, we would have the variance here. Here, what we get is the Efronstein estimate of the variance. Okay, so again, this is somehow very nice and appealing. For self-bounding functions, we get, again, for free, we get exponential tail inequalities. Okay, so this is, for the lower tail is purely Sub-gaussian, and in the upper tail we have the same corrective term that we had in Bernstein's inequality. Okay? So in particular, if z is just the sum of indicator random variables, in the special case when z is a sum of Bernoulli random variables, right? So these xi's are 0, 1s. Now this is of course a self-bounding function, right? Because if I leave out one variable, then the value of the function can only decrease. It can decrease by at most 1, and the sum of these changes is less than z itself. Okay, so this is when the xi's are either 0 or 1. So this is an example of a self-bounding function. For this example, if we plug it in here, then this is exactly Bernstein's inequality. So what these inequalities say is that somehow what matters, the reason why we get Bernstein's inequality is because of the self-bounding property. And this is true for all possible self-bounding functions. Okay? So this is really nice because now we have basically the sharpest possible kind of inequalities for lots of examples. Random VC dimension, the conditional Rademacher averages, and so on. Okay? And of course, we saw why these examples are important in machine learning, because these are random quantities that we can measure, and what these inequalities tell us is that these quantities are really close to their expected value. The probability that it's far away, it's much farther away than something like the square root of the expected value is tiny. It goes down exponentially. Okay? And this is of course very good news, because what this means is that what you see is what you get. What you can measure on data is really the close to the expected value. So whenever we can say something like this on something that we measure on data, that it's concentrated, then we are happy. Then we know that the random fluctuations can't work against us. At least they will only work against us with tiny probability. Okay? So this is the example of self-bounding function. This is what I just mentioned. And there's this whole class of self-bounding functions that we call configuration functions. Right? So when the value of the function is witnessed by a subset of the sample, and then they have this kind of property. So there are many examples of configuration functions. All right. These types of bounds were first derived by Talagrand using completely different methods. Okay. Now sometimes these conditions are a little bit too rigid. Right? So here we really need this bounded differences assumption, and then that's how we bound the Efronstein estimate of the variance. Okay? But sometimes we don't have this, and but we have something like this. We do in some applications we do have that the Efronstein estimate of the variance is bounded by, if this b was 0, then this is just, and a was 1, then this is just like in the case of self-bounding functions. Well, this is a little bit more general. Okay, it's my linear function of the value of the random variable itself. Okay. So when we have something like this, then the Efronstein inequality tells us that the variance of z is less than a times the expected value of z plus b. Okay? We call these weakly self-bounding functions. Okay? So we don't have now the bounded differences condition. We only have this. All right. Okay. And then we can still get something like what we had before. Okay. So for the upper tail, so for probabilities that z is larger than its expected value plus some constant t, then this is less than, and this is again what we would expect. This is like in Bernstein's inequality, and here where we would have the variance term, well, here we have just the Efronstein estimate of the variance. So this is even true under this more relaxed condition. Okay? For the lower tail inequalities, well, we need something more. We need that at least these differences are less than or equal to 1. We don't need them to be positive. Okay. And then you get something. The exact form is not so important here, but it's morally it looks like Bernstein's inequality again. Okay. So for weakly self-bounding functions, we can use this kind of machinery, starting from modified logarithmic Sobolev inequalities, arriving at some differential inequality for the moment generating function, solving that, and then getting this. Okay, so this is somehow This is the main idea of deriving concentration inequalities of this type. Very often what we get is sub-gaussian inequalities when the variance term is replaced by the Efronstein estimate of the variance. Okay? This is nice because there's a lot of room to play. So these are not the only examples. And then you can just go and try to tweak the machinery and get your own concentration inequalities. This is somehow a method, and then you can play with that method and maybe get what you want if you know something else about your random. Okay? Yeah?
Last term, is this C subscript C or something?
This is C minus. C minus is just the negative part of C.
Oh.
Okay, so if this number is positive, then that term is not there. If it's negative, then if this is negative, then you just have the absolute value. So it's strange. Somehow, sometimes you get a purely sub-Gaussian inequality. The lower tails are strange, like in the previous case. The lower tail was completely purely sub-Gaussian. Okay, so this is somehow lower tails are nicer when we talk about positive random variables. These are of course positive. All right. Now, I must, in any course on concentration, Talagrand's name must come up in a prominent way, because his work was the great breakthrough in the 90s. He came up with his completely somehow unique way of thinking about this problem, which was based on this isoperimetric view. I will only show you the very basic way of thinking about this, and then he also came up with an inductive method that is completely elementary. You can read the proof and understand it line by line, but somehow the big picture is very difficult. So somehow nobody knows how he got them. He got incredibly sharp inequalities. For example, for configuration functions, for many examples, suprema of empirical processes. He got very nice. But then people started to try to come up with their own proofs, because those were somehow intuitively not clear what was going on there. Okay? And for example, Michel Ledoux was, when he introduced this method, this kind of method, this is what he was trying to do, come up with an understandable proof of what was going on. And of course now, after another 15 years now, we can even do more in some cases than Talagrand. Okay. Anyways, it's probably because he stopped working on this problem and he's working on spin glasses. Anyway, so this is the isoperimetric point of view. So what do I mean by isoperimetric? The classical isoperimetric problem asks you if I give you any set on the plane with a given area, what's the set that minimizes the perimeter? Okay, and the solution of that is the ball, is the circle. Okay, and in d dimensions is the same. Given any set of a given volume, the one that minimizes the surface area is the Euclidean ball. Okay, so that's the classical isoperimetric problem. You can equivalently rephrase this in saying that if I take any set and I look at the blow-up of this set. So what does it mean, a blow-up? I look at the set of all those points which are within distance epsilon of the set itself. Okay, so then I get this set A sub epsilon, right? for some epsilon. Now, given any set with a certain volume, what's this? So if you are given the volume of the set, which is the set which minimizes the volume of the blow-up? Okay, this is an equivalent way of asking the isoperimetric problem. And the nice thing about this is that here we don't need the notion of a surface area anymore. So in particular, you can ask this question in any metric space, right? Because all you need here is distances, well, and volume. Okay? So if you have a notion of volume, given the volume of a set, so we have a measure, given the measure of a set, what's the set which minimizes the volume of the blow-up? Okay. In a Euclidean space, the solutions are exactly the same. Okay. So this is somehow the isoperimetric point of view. Now we go in this space, x to the power of n. This is the space where our independent random variables live. Okay. And we take any subset of this product space. All right. And now we want to say how far is this vector from this set. If this set is completely abstract, it doesn't need to have a natural distance on it, then we can still go to the Hamming distance. Okay? What's the Hamming distance? The Hamming distance says that how many components of x do I have to change such that I get in the set. Okay? That's the Hamming distance. So the Hamming distance of a vector y and the vector x is just the number of components that are different. Okay? Now given a set, I can now ask what's in that set, which is the point for which this Hamming distance is minimized. Okay? This will be that point y will be the closest guy to x, and this distance is called the Hamming distance. Okay? So I have a set. This is my set A, and I have a point x, and now I ask how many components of x do I have to change so that I get in here. Okay? This is the Hamming distance. All right. Now, Talagrand's inequality says that if I take, well, this is not Talagrand's inequality. This is a very easy inequality, which is somehow the isoperimetric way of looking at a concentration. So now, if I take a random point in this set, and by random I mean that independent components. The components don't need to have the same distribution, but independent components. Then the probability that the distance to the set is large is very small. What does this mean? It means that, for example, if this set A that I'm looking at is not too small, think about now sets, let's say, with the probability that x is in A, let's say this is something like 1/2, or a constant. Let's say it's not too small. Then the Hamming distance will be small. It can never be larger than square root of n. The probability that it's larger than square root of n plus t goes down exponentially in a Sub-gaussian way. It's less than e to the minus t squared divided by. So it means that if, no matter what set you give me, if it's not too small, let's say it has a probability around 1/2, or a constant, the probability of the set is in here. If this is a constant, then a random point, we only have to change square root of n components to get in that set. And this is true in any metric, any space, any measurable space. In a product space. It's important that the x1 and xn are independent. Okay? Let me show you the proof. Right? This is called the concentration of measure phenomenon. It means that if I look at this set A, which is not too small, let me draw another picture, but it's not going to be much more interesting. So this is our set. And now if I blow this set up in the Hamming distance by something like a constant times square root of n, okay, so I can change square root of n components. The square root of n is a tiny, tiny, tiny fraction of all the components. Okay? Then this new set, A epsilon, or A c log n, c root n, is almost everything. Right? The probability of this blow up is huge. The probability that a random point is outside of this blow up is exponentially small. Okay, so this is concentration of measure. If you take any set of a constant probability, and we blow it up by just a tiny bit, by square root of n, right? Let's say 10 times square root of n, then what we get is that whatever is outside is something like e to the minus 100. Really, really small. Okay, yes?
Is there any assumption that we only take compact sets and we cannot find any conversion set out of a compact set?
There's no metric or topology here. This is these x and n's are arbitrary sets. So all you need is that you can define a probability measure on it. And the only assumption is that we have independent components. Apart from that, there's nothing assumed. Yeah, we're only looking at this. This is not real distance. This is not metric distance. This is a Hamming distance. How many components do we have to change such that we get in this? Okay. So this is kind of surprising and beautiful. And this is called the concentration of measure phenomenon. Okay. All right. Yeah, I said it here. And the proof is here on this slide. It's really easy now. We can prove it in 5 minutes. So we will use the bounded differences inequality. Let's just look at this random variable. Right? I take now a fixed set, A, and I take a random point, boom. With property 1/2, that point will be inside already. Right? Because let's say that the probability of A is 1/2. For now, it's not so important. But with probability 1/2, it's inside, but with probability 1/2, it's somehow somewhere outside. Okay. Now let's look at the distance, right? The Hamming distance of this point to this. This is a random variable. Okay. Now this random variable has the bounded differences property, right? Because if I change one component, then this random variable for sure cannot change by more than one. Right? This is the bounded differences property, and therefore, by the bounded differences inequality, the probability that it differs from its expected value by more than t is less than e to the minus t squared divided by n. Okay? The n is now the sum of the, remember, we had something like the probability that z is greater than the expected value of z greater than t is less than e to the minus t squared divided by the sum of the ci squares. Right? The ci is by how much the value of the function can change if I change one component. Now here the ci's are 1, so this thing here is equals n. Okay? So that's how we get this. Right? Now I'm looking at the lower tail first. Okay? Good. Now this is true for all t's, for everything. In particular, I can look at what happens when t equals the expected value. Right? So when t equals the expected value, then what's this probability? This is just the probability that the distance is less than or equal to 0. Okay? But we know what this is. What's the probability that the distance is less than or equal to 0? Well, the distance is non-negative, so that means that the probability equals 0. That means that we are in the set. Okay? So that probability, this probability here, when we take t like this, then this probability here is just the probability of A. Okay? Let's say 1/2. Right? But then what this inequality says is that the probability of A is less than or equal to e to the minus twice t squared. What's t? Is the expected value squared divided by n. So now we get, this gives us an upper bound for the expected distance. If you rearrange this inequality, right, what we get is that the probability of A is less than or equal to e to the minus twice the expected value of b squared divided by n. If we rearrange this inequality, then what we get is that the expected Hamming distance is less than square root of n times log 1 over pa. This is already nice. This already tells us that the expected distance is small. It's at most square root of n. Okay? And then to get the inequality I showed you on the previous slide, well, we just use the bounded differences inequality again, because it says that the probability that the distance is greater than its expected value plus t is less than this quantity here, but the expected, we know that the expected value is less than this, so I can put this quantity here. Okay. Yeah, so we just use the bounded differences inequality twice, and we see this very nice property. Okay. All right, so far so good. Okay, but now Talagrand showed that one can do much, much more than this. Okay, and he also showed how this type of inequalities, an inequality like this, can be used to prove concentration inequalities for functions, for like Lipschitz functions. Okay? In fact, I didn't prepare a slide on that, but you can easily show that if this is true, then you can derive from this inequality the bounded differences inequality. These are completely equivalent. Okay? And this is really not difficult. You can go back and forth between the isoperimetric way of looking at things, distances, Hamming distances to sets of a random form, and concentration of functions with bounded differences. Okay? But then what Talagrand showed is that we can go further. And so the first step is we can repeat the exact same argument for weighted Hamming distances. So what's a weighted Hamming distance? Well, now each component of the vector x has a weight. Okay? And these weights are given by this vector alpha. Okay? So the first component has weight alpha 1, the last one alpha n. Let's say these are non-negative. Well, I don't care because I put absolute values. Now, typically, we will require that the Euclidean norm of this vector is 1, but this is not necessary as the way I wrote. Okay? And now the weighted Hamming distance is just, I look at all those components where x and y are different, and I sum up the corresponding alphas. Okay? This is the weighted Hamming distance. Okay? And then the exact same argument as before shows that the probability that the weighted Hamming distance is greater than t plus, now instead of n, right? We have now the norm squared of alpha. So the previous example corresponds to a case when these weights are equal. They are all equal to 1. Okay? So then we had n here. Now instead of n, we have the norm squared of alpha. Okay? And that's less than or equal to e to the minus 2 t squared divided by the norm squared of alpha. So this is just a generalization of the previous, of this inequality, where the ends are now replaced by the norm squared of this weight. Okay? The proof is exactly the same. So I can rewrite this. And if we restrict our attention to vectors whose Euclidean norm equals 1, clearly I can do it because everything only depends here on the Euclidean norm of alpha. So we can just only look at weight vectors whose Euclidean norm is 1. And then you can rewrite this, that for all vectors of this type, if I look at either the set is small, or if the set is not small, then the blow-up is very large. So everything that's outside of here, right, this is the probability of the complement. The probability that the distance, the weighted distance is greater than t will be small. This inequality can be rewritten in exactly this way. Okay? So either the probability of the set is very, very, very small, or if it's not small, then this will be very small. Okay? You can see that's what this inequality is. Okay? And we just proved that this is true no matter how we choose the weight vector. Okay? Now Talagrand showed a wonderful thing, that this supremum can be taken inside here. And that has very, very far-reaching consequences. So let me describe you how this goes. This is the famous convex distance inequality of Talagrand. Okay. So he said that let's define a new distance, which is now we are taking all possible weighted Hamming distances, all possible weight vectors of norm 1, and I'm taking the largest one of this. Okay? So this distance is typically, it should be much larger than any weighted, than a typical weighted Hamming distance. Okay? In particular, I can, the weight vector can depend on x. Right? I can choose this weight vector. And then he showed that either this probability is small, and if it's not small, then the blow up of the set in this much stronger distance is still small. Okay. This random variable is much larger than if I just take one particular alpha vector, let's say a uniform alpha vector. Okay. And this inequality tells us that this guy is still small. Okay, so it's not clear, when you look at it like this, it's not clear why this is so important. But we can see that it's clearly much stronger than this type of inequality. Okay? We can prove it easily today. So he proved it by a very refined induction method, completely out of the blue. But now we can prove that the square of this distance is a self-bounding function. It satisfies this inequality. Okay? It satisfies that if I leave out one point and I look at the distance squared, then it's bounded by the value of the function, 4 times the value of the function itself. D is 0 here. Okay? So then we can use this type of inequalities, and this will imply Talagrand's inequality. Okay? It now follows from, we can prove the convex distance inequality in this way. Okay? All right. And, well, okay, maybe I should mention this. The basis of the proof, so how do we prove that it's that the square of this distance is a self-bounding function? Well, we need to use, so let's look back at the definition of the, where is it? Oh, yeah. So let's look at the definition of the convex distance. So the convex distance of a point to a set equals, so we have the maximum over all alpha vectors with norm 1. Let's write it like this, alpha vectors with norm at most 1 of the minimum over all vectors in A of the weighted Hamming distance, right? And this is for all the i's when yi and xi are different. This is the convex distance. This is the convex distance. Now, whenever we have a max min, then we think about the minimax theorem. For the minimax theorem, well, we would need this minimum to be over a convex set, and this is not convex at all. But this is equal to if I take the infimum over all measures on alpha, on the set alpha, over all probability, all possible probability measures on the set. Okay. And now here I can write, I can just write the probability that if I draw y with respect to this measure I, then this is the probability that yi is not equal to xi. Okay? I can rewrite the convex distance inequality like this. And now I can use the minimax theorem. Okay? The minimax theorem says that now I can replace the order of because if this is a convex set, this is a convex set, you can show that this function is convex concave. Okay? So we can use the we can flip this order, and then you can easily show that the sub-bounding property, this property holds for the square of the convex distance. Okay, so it's not completely trivial to prove this, but it follows from the minimum. Yeah? Okay. So let me show you how this convex distance inequality implies something that we have already seen. Okay, so I want to tell you about convex Lipschitz functions. Okay? We have already looked at convex Lipschitz functions, so we have we will consider a function f which is defined on the cube, in the n-dimensional cube, and takes values in R. Okay? And we will assume that this is a Lipschitz function, and now we will take independent control. Remember that we already showed somewhere here that this function has this generalized bounded differences property. So in particular, we have a nice upper tail inequality at this time. Okay, so let's rewrite this, and we will actually get a little bit more, because this argument will also give us a lower tail inequality. All right. So let's just look at now a subset in this metric, in the cube. I wish I could erase this easier. So now we are in the cube, and we have a set A. All right. So fix any set A in here, and let's look at now the Euclidean distance. So capital Dx A is the Euclidean distance of any point to this set. Okay, so this is not Hamming distance anymore, but Euclidean distance. All right. Now, if the set is convex, then this Euclidean distance is always less than or equal to Talagrand's distance, to this convex distance. Okay, that's our main lemma here, and this is easy to show. Okay, so here's the proof. The Euclidean distance of a point to a set, well, I'm using the same trick here. Right? Instead of saying that this is so what's the Euclidean distance? Let me write it. This is defined as the infimum over all y's in the set A of the distance between x and y. Of the Euclidean distance between x and y. Okay. But if the set A is convex, then I can replace this, I can minimize over all distribution. I can draw randomly a point in the set, and now look at the distance, and now I can look at all possible probability measures on the set. Okay? So see, this is where we use convexity. If the set is convex, then I can rewrite like this, the Euclidean distance. Okay? And why is this good? Because I want to use again the minimax representation. Now, this difference is always less than or equal to this difference. So here we just have the probability with respect to y, or that these two guys are not the same. Why? Because the distance between the difference between xj and yj is always less than 1. So I can upper bound this by, if they are not the same, I upper bound this by 1. The distance cannot be more than 2. Okay? If they are the same, then of course it's 0. If their distance is 0. If they are different, then their distance is less than 1. So that's the only thing we use here. And now, because I can use the Cauchy-Schwarz inequality here, right? I can represent this square root as this norm squared as the maximum with the inner product of any vector, any unit vector, okay? And this is, by the minimax theorem that I just mentioned, this is exactly Talagrand's distance, right? We get exactly the same formulation that I wrote. Okay? So with this trivial inequality, absolute trivial inequality, that a distance between two numbers, both of them are between 0 and 1, is always less than 1, we get this nice little fact, okay? Good, so now how do we use this to get the concentration inequality? And this is where the isoperimetric view kicks in. This is very easy. Yeah, so here's the theorem. But let me show you the proof, and then we will discuss the theorem. So now I have a Lipschitz function. Okay, so f is now a Lipschitz function defined on this cube. All right. And we want to say something about concentration of this. Okay, so what do? Let's look at level sets of this function. This is a convex Lipschitz function. So let's look at the set of all those x's when this function is less than some number s. Now this is a convex set, right? If the level sets of a convex function are always convex. Okay, good. Also, f is Lipschitz. So if I want to look at the value of the function at some point, then it is at most the distance of this point to the level set at level s plus s. Because if we are, so let's say this is it should be convex. This is a sub s, and I know that in this set the value of the function is less than or equal to s. So if I want to say something about the value of the function at this point x, then the f of x, well, how far do I have to go to get to s? Well, that's just the distance. This is the d of x and a. And the function cannot grow from here to here by more than the distance. That's the Lipschitz property. Okay? So f of x is less than or equal to the value of the function here, that's s, or less than or equal to s, plus this distance. Okay? That's what's written here. Okay? So this is the way of converting concentration of measure inequalities of this type to concentration inequalities for Lipschitz functions. So if you have a Lipschitz function, then this is less than s plus the Euclidean distance, but that's less than s plus the Talagrand distance, the convex distance, right? Because of the previous level. We saw that if we have any convex function, any convex set, then the Euclidean distance to that set is always bounded by the convex distance, Talagrand's convex distance. And that's it. So now we can use the convex distance inequality, right? Convex distance inequality tells us that the probability, what was the convex distance inequality? It said that the probability of any set times the probability that the distance to this set, of a random point to this set is greater than t is less than e to the minus t squared. Okay? So we can just use it here for the set A sub s, right? This is the set A sub s. This is the set A sub s, and this is just the probability that we are outside is bounded by this. So this product is less than e to the minus t squared divided by 2. That's the convex distance inequality. Good. Now, take s to be the median of the function. So if s is the median, then this guy is 1/2, right? So then what we get is that the probability that f is greater than the median plus t is less than twice e to the minus t squared divided by 2. That's written here. The probability that the value of the function exceeds the median by more than t goes down exponentially. And if I take the value of s to be the median minus t, then here I get the median minus t plus t. So this is the median, then this is 1/2. The probability that the value of the function is greater than or equal to the median. This is 1/2. And here I get the probability that f is less than the median minus t. That's this inequality. So we get both tail bounds. We didn't get this with the previous method. The convex distance inequality implies that if we have any convex Lipschitz function, then it is concentrated around the median. But if it's concentrated around the median, it's also concentrated around the mean, because in this case, the median and the mean, the distance of the median and the mean is less than standard deviation, which is a constant here. That's easy. So this is less than, I don't know the right constant here, but for sure it's less than. Okay? So when you have concentration inequalities around the median of this type, then you can also derive concentration inequalities around the mean the same way. Okay. Any question about this? Okay, so I hope I could show you how this isoperimetric view and Talagrand's convex distance inequality is powerful. Basically, whenever you want to use it, all you need is to bound something that your function has by the convex distance, and then use the convex distance inequality. Right? So the key inequality here was that the value of the function is less than s plus the convex distance inequality from any set. And from that, we got what we wanted. And there are many applications of the convex distance inequality for very different things. So, for example, Talagrand was the first to show inequalities for self-bounding functions using this. And all you need is that if f is self-bounding, then you can come up with a reasonable. And there are many other examples, ranging from examples like if I take n points at random in the plane, and now I want to look at the length of the minimum spanning tree. The total edge length of the minimum spanning tree. He could get concentration inequalities, very sharp concentration inequalities using this. Okay? Or you can also handle beam packing, optimization problems like the beam packing problem. If I have x1, xn, these are independent random variables taking values, let's say 0 and 1, and I have now bins of size 1, and the question is how many can I pack? What's the minimum number of bins such that I can pack all these numbers in such that there's no overflow? Okay? This is a very complicated optimization problem. And using the convex distance inequality, we can get very sharp concentration results for the number of bins, which is a very complicated random variable. It's the number of bins that you. So there are lots of very interesting applications of this. In random graph theory, this was another huge breakthrough of this type of inequalities. And there are many applications. Empirical process theory and so on. So I suggest we take a break, and after the break I will show you a couple other things.